talked about the Perseverance launch, the instruments aboard. We've talked about infrared astronomy. And all of this kind of suggests that all that NASA does is look outward. And I think it's really important that we focus on the fact that actually much of NASA's research is looking down, is looking upon our Earth, our home, that we need to protect, that we need to understand, and yet is still actually quite a mystery. With all of the science that we've done and all this popular exploration of, living on Mars and going out so far and all this, really, there are enough mysteries for us here at home to explore. We have a great guest today who's going to talk to us a little bit about this, a close personal friend and someone that really opened up a lot of opportunities for me to understand this better as we actually went on an expedition with the Ocean Exploration Trust aboard the EV Nautilus. And this gave me an opportunity to see what I think is critical for kids to understand these days as they explore careers in science, which is that when you have a job in science, first of all, you have no clue what you're getting into, right? Any class you take in school really only scratches the surface of the kind of jobs that are out there. But second of all, no one scientist works alone. And that's really what I took away from working on the Nautilus for that short time, was that all of a sudden all these geologists and oceanographers and chemists and engineers all came together to do some pretty amazing things. So we're very, very lucky today to have Megan Cook, who is going to talk to us about the research that Nautilus does, both kind of aligned to some of the things that we've done in the past with NASA and over the broader kind of scope of understanding our oceans. So without any delay, let me tell you quick, we're going to hear a little talk from Megan. We'll do some Q&A, and then we'll finish off with some education resources from both the OET and from the JPL education teams to help you guys kind of push this further. If these are things that you enjoyed and you have kids at home or students who really want to explore this, we have some resources for you. In fact, we'll even follow up on a Saturday session just for teachers that will, again, feature Megan coming back for a second time. We'll be able to, again, just look a little bit deeper in terms of what we can offer students and teachers in this space. But first, let's pull the curtain back for the wonderful Megan Cook. Please take it away and tell us a little bit about the Ocean Exploration Trust.
Thank you so much, Brandon. I am so excited to be here and to get to share some with you today. I'm Megan Cook. My pronouns are she and her, and I'm connected with you here today from Friday Harbor in the state of Washington. This is the ancestral and modern homelands of the Coast Salish people, including the Suk, Samish, Saanich, Semiahmoo, Songhees, and Lumbee nations, and I thank them for stewarding this wonderful place surrounded by a beautiful ocean. And that's what we get to talk about today, is the ocean and this blue, salty planet that we all share. I'm so excited to bring the topic a little back closer to home, a little closer to the blue backyard for everyone to talk about oceans today. There are fascinating discoveries being made to the extents of the known universe, and there are fascinating discoveries being made right here. Basic discoveries, basic understanding of the things that we have right here on the planet. And I'm really happy to be able to share that with you. In our community, we sometimes call this the exploration of inner space instead of outer space. And so I feel really honored and really special to get to share some of that on an official NASA program like this. So some basics. Our oceans are super essential to life on this planet. If this is new to you, I'm happy to share that the ocean has been making 50% of the oxygen that we all love to breathe. It regulates our climate and our water cycle. The oceans provide protein for billions of people. They transport 90% of the things that you own. So if you've never been on a journey across the ocean, many of the things in your house probably have. So they're essential to our transportation and infrastructure. They're full of potential of things like biopharmaceuticals, where we can learn from nature, incredible novel things. And they're a source of meaning and mystery in art and in culture. And it's some of that mystery that I want to dive into today and what my team gets to help reveal. For all that we do know about the ocean, all these fundamental things, there's a lot that we don't know. And there are some big numbers that still blow my mind every time I hear them, that the ocean is 95-ish% unexplored, and the ocean is 80% not mapped. It is only 20% mapped at modern resolution. I'm going to talk a little bit about the technologies and tools and how we're chipping away at those numbers and how you can be part of chipping away at those numbers too. And I'm really proud to be part of the team at Ocean Exploration Trust. I'm the manager of education partnerships and programs for this nonprofit. And I've been part of the team for 8 years. Since I'm the one giving the talk, I get to pick out some of my favorite moments of discovery to share with you, to introduce you to the things that we've seen along the way. There are way too many, an embarrassment of riches to choose among all of them. So I hope I'll give you a few more and spark your curiosity to go and explore some others as well. So we want to kick it off with slide number 1, and this is our spaceship. Ocean Exploration Trust owns and operates exploration vessel Nautilus. She's a 211-foot long research vessel. And this ship travels around the world supporting our mission to do 3 things. The first one is explore. Go places we have not seen before on planet Earth. The second part of the mission is to innovate and develop and test technologies. The parts of the ocean that are unexplored are not generally the parts where you can put on a mask and fins and snorkel and jump into the ocean and check them out. They are the parts of the ocean that are deep and dark and far from shore. And those are places where we get to test out really interesting technology suites to crack those codes, solve those problems. And the third part of our mission that is nearest and dearest, certainly to my heart, is to inspire with these expeditions, to share them with the world, and to invite another generation of explorers to be part of them. We do that by broadcasting 24 hours a day, 7 days a week from the deep sea, to invite you into the process of exploration, to demystify that somewhere. And to let you know, the ship is at sea right now. We are doing a little bit of every STEM professional's favorite task right now, which is troubleshooting. So hopefully we'll have the chance to chat with a member of the team a little bit later. But if not, you can tune in to Nautilus Live and see this ship out exploring the ocean right now. On slide number 2, I get to talk with you today. It is my total pleasure, but I would be remiss to not acknowledge and first highlight the incredible team that does this work. We call our team the core of exploration. They are not only scientists, but engineers, technology specialists, data managers, media specialists, educators, students, professional mariners. It runs the gamut. There are 1,200 professionals who have sailed in our core of exploration over the 10 years that we've been on this mission. And I think this is one of the most exciting things for students, as Brandon mentioned. When I was a kid growing up, I grew up in the desert. The ocean lived only in storybooks. And I thought being a marine biologist was the only thing that meant you could work in the ocean. And now I get to spend my whole career telling people how many other things they could do that could still end up taking them to these places. Let's jump into that exploration. Slide 3, let's talk about where we want to go explore. The ship has moved all over the world in the time that we have been an organization, the last dozen or so years. But we just received a new federal award through the Cooperative Institute system to work with partners to explore and characterize America's oceans. This is the 50% of America that is underwater. Every nation has sort of you can imagine it like a donut around your shore. It is an exclusive economic zone, a buffer of 200 nautical miles, and that is part of the country that shares that maritime border. So America has 3.4-ish million square miles of ocean, and that is half of the total territory that is America. And we have basic questions. What is there? Who lives there? What kind of habitats do we have? What kind of history, shipwrecks, maritime heritage is there? And we're on this mission to go and explore that. In slide 4, our model of exploration really centers around telepresence, which is a suite of transmission technologies. It's the same way I'm talking to you right now, but it lets students FaceTime with a robot at the bottom of the ocean. It takes a data signal from the remotely operated vehicles on the seafloor, not only just up to the ship, but out through a satellite feed and to ground stations, out through the internet to anyone who wants to be there at the moment of discovery. If you have seen, if you can kind of imagine some parallels here to the space sphere, we certainly can think about a shoreside support team, an operational team, whether they are in orbit or out at sea, and then a robotic end effector like a vehicle. We're really proud to have been able to use this technology not only to explore the oceans, but also to work with NASA. We got to work with the SUBSEA, love a good acronym, the Systematic Underwater Biogeochemical Science and Exploration Analog, SUBSEA, team from NASA Ames, to collaborate on a study where looking at these different parts and introducing latency in the gaps in between each of those different segments. How do you help a team be effective in your exploration mission? How can you work together and break down some of the barriers that, now that we live in a digital world and anybody's lagging on an internet call, how much that latency can be frustrating. Certainly when we want to explore an ocean or explore a solar system, we want to work around those problems first. So really happy to see our first parallel there with space. In slide 5, I want to give you a quick intro to seafloor mapping. It's very difficult to know much about the ocean or to ask a good scientific question about the ocean if you don't have a map, if you don't even know where we're starting. So the first part of our exploration mode is to map the seafloor. We use a multi-beam map, a multi-beam echo sounder, which is an acoustic tool. You can think about this like shouting at the seafloor and waiting for the echo to come back and revealing the landscapes along the way. On slide 6, I want to introduce you to some of the shapes of the seafloor. If you've never considered before that all of the rough and rugged parts of the dry, dusty parts of Earth, mountains, valleys, open plains, are underwater, let me introduce that topic to you. The Earth is just as varied in the salty parts beneath the ocean. The world's largest mountain range wraps around the Earth like the seams on a baseball. And we see all of those same features, valleys, hills, open plains, deep trenches in the ocean. And a mapping system like this reveals it. I often ask with students, between the blurry part that you can see on the left, and that is a satellite approximation, that's an unmapped segment of the seafloor, versus that richly colored, that is a false color scale, that rainbow colored seafloor there where you start to see all those different shapes and different features. I could ask a lot more interesting scientific questions based on the part that's in detail there. And it would lead me to be much more curious about what's happening there on the seafloor. The second part of our exploration suite of tools and technologies, though, is on slide number 7, and that is our team of remotely operated vehicles. I always laugh that this photo looks a little like they're going to drop an album, but these are our 4,000 and 6,000 meter rated vehicles, which are, they all have names, and they have names from classical mythology for any of those English language arts educators out there. These are Hercules and Argus, Atalanta, and Little Hercules, because we need a little more creativity. On slide 8, though, I want to introduce you to Hercules. This is the typical vehicle, the remotely operated vehicle. You can think about this like robots on leashes down on the seafloor. They are connected to the ship at all times, and they send us back data from a suite of different types of tools and cameras that we can put on or take off depending on the needs of that mission. So we have things that can, like 2 manipulator arms, collect physical samples from the seafloor. We can collect water samples, profile the water, collect gases or minerals out of concentration, all kinds of different types of tools that allow us to explore these different sites. All right, that's enough of like the nuts and the bolts of how we do this. Let's talk about some of the cool things that we get to see. On slide 9, I want to introduce you to one of our, I guess our discoveries often fall into sort of these very broad categories that with sort of these artificial boundaries in between, right? We think about geology, and then we think about that being different from biology or chemistry. Everything I'm going to show you is a mix of everything. But if we're going to call it arbitrary boundaries, let's talk geology. What you're looking at is a hydrothermal vent chimney. This is a place where the skin of the planet pulls apart at a tectonic boundary. Water from the water column seeps down into the rocks and cracks, is heated by the magma chamber underneath, dissolves rocks and minerals along the way, and this superheated water comes rising and shooting back out as that black smoke or as a plume rising out of the seafloor. I am trained as an ecologist. I am a biologist at heart, and the first time I dove on a hydrothermal vent, I about lost my mind. These are as big as like 7 or 10-story buildings. They are hundreds and hundreds of degrees, and it's just spectacular. If I was going to pick a superpower, I think I would want to fly. It would be the one I would pick. And maneuvering a remotely operated vehicle through a scene of chimneys like this is as close, I think, as that like flying experience I will probably ever get. What's spectacular about these, besides the fact that they're these mineral-rich copper, gold, zinc, silver, rich landscapes underwater and their sheer scale, is that there's life there. This is the site we first discovered chemosynthetic life, chemosynthetic being that foil to photosynthetic. Chemosynthetic meaning rather than using sunlight to make energy, you are going to use chemicals and transform that in a chemical process into sugars, life there on the seafloor. Slide 10, we really opened up our understanding by discovering hydrothermal vents that there were different methods ways to make a living in this universe. And we've now, this is, thank you NASA, an image from Saturn's moon Enceladus, where it is very likely that we have hydrothermal activity beneath the ice-encrusted ocean. So these lessons that we're learning here about our own planet are kind of widening the perspective of ways that we can look for life, and we can look for these different types of planetary processes outside of our own planet, which is really, really exciting. So there's a lot of crossover between the ocean and space science communities looking at ocean planets beyond our own. For slide 11, I want to introduce you to another of my favorite chemosynthetic environments, because I never knew I was going to have favorite chemosynthetic environments until I had the chance to work with this team. This is a brine pool. There are lakes underneath the ocean, y'all. This is a hypersaline, so regular salt water, again, gets down into the cracks in the seafloor sediments, into salt domes, which are created by plate tectonics and changing ocean depths over time, and dissolve some of that salt concentration into supersaline brine, and can get captured in depressions and domes, spots in the seafloor, and form these lakes, which are hot spots of biodiversity and an incredible place to look for extremophiles that make a living in these very, very tough conditions of not only high pressure, extreme cold, but add hypersaline into the mix. And you get some really interesting life like the mussel and clam beds. You can see some different sea cucumbers, crabs, as fish communities all living vibrantly down here on the seafloor. If we want to pretend biology hasn't been present yet, let's talk about some more biology of the seafloor. On slide 12, I want to introduce you to some deep sea corals. This is a Iridogorgia, or a spiral coral. It is over 6 feet tall. It is more than a Megan tall. And these are individual colonies, so you are looking at an animal. You are also looking at an animal that is like the trees of a forest, the creator of habitat complexity on the seafloor. There are incredible coral communities all throughout the deep sea. Not typically the reef-forming ones that we'd often think about from a tropical vacation or a planet Earth special, but these highly dynamic and incredibly old species. The deep sea is a place where a lot of metabolism moves very slowly. And there are coral colonies. This one is likely over 1,000 years old. There are corals in the deep sea that are over 4,000 years old. And if you want to think about that, like what was happening on Earth 4,000 years ago? Humans invented glass. We found out how to make glass. So an individual animal is older than glass. And, you know, the Babylonians invented a base 60 math system 4,000 years ago and divided a circle into 360 parts for the first time. So like that individual organism is older than math, which is pretty startling to tell students. And then I just wanted to share that one of the things I love the most about exploring the deep sea is we're constantly being surprised. You know, you can never let your guard down. It doesn't matter when in the expedition it is, the next thing right around the corner might be the last thing that you ever expected. And on slide 13, I want to show you one of those moments where I, after 8 years of this, got caught completely off guard. This was the last expedition of the year last year. It was the last few hours of the dive. And we were on our way across a sedimented basin, trying to get over to some other rocks to take a look. And there was a sonar target off in the distance that we thought was likely a pile of rocks. And as we advanced upon it, it was certainly not a pile of rocks. This was a whale fall, absolutely covered with life. A whale fall is kind of a made-up word, I guess, but you can put the parts together. It is when a whale dies and sinks or falls to the seafloor, and the dinner bell goes off all across the seafloor community, and in come all these different kinds of life. And scavenging this carcass on the seafloor were amphipods, eel pouts, the most metal, bizarre, amazing creature, which is a bone-eating worm. Ossidax is the genus of worms, and amazing to think about a community ecology. How do they find these whale falls and hop from one to the next across the deep sea environment? But they eat and digest the calcium of bones, and that's what you can see. Another chemosynthetic community there living in the sediment off of the plumes. We had no plans to study a whale fall during this expedition. In fact, we just wanted to go over to the rocks, and we thought we would be like headed back to port. So you hit the proverbial brakes at these moments. And what the system of telepresence allows us to do is call up the experts. Who do we need to see this discovery right now? Whose expertise could help us better understand this? And how can we contribute more to the science community than just looking around at one another of whoever was on board at that moment and being like, I don't know, Brandon, what do you know about whales and what type this might be? So it's kind of an acceleration and also a flattening of the process of science that we're able to include more people at this moment. This was a big discovery. There are whale falls that have been found when they're in a highly digested state. There are a few whale falls that have been intentionally sunk to study their progression over time. But just finding one like this in the moment really inspired a lot of scientists. So we wanted to come back and see that. I want to take you to slide 14. We went back just a few weeks ago and returned to the whale fall a year later to see what was there. There was a lot less there. Spoiler alert. So as we looked at that, there was a community really succession there. There were different types of worms and different types of microbes on the seafloor. None of the larger scavengers were still there. Well, one rat-tailed fish that we're not totally sure if we just caught him on the flyby or if he or she were hanging out there. But you get to see just these like very surprise moments that there's now a time sequence for this particular site in the deep sea. And these are these basic catch you off guard, never know what's around the corner next kinds of moments that a ship of our kind has. This year has been a really different year for us. On slide 15, I want to show you some of the sites where we've been this year. We've changed a lot about our program, but I'm incredibly proud of our team for finding a way to make a safe operation season this year. We have asked people to go to sea for longer. We've extended the duration. We quarantined and tested the entire team, and they're all aboard wearing masks to make it possible to be out there. We transferred a lot of our science effort through telepresence to involve people leading expeditions and leading dives and sampling from shore through the internet. But an amazing gratitude to the team who are out at sea right now. And I want to bring in part of our team right now. I can see that one of our seafloor mapping specialists and watch leaders, Erin Heffron, is here with us live aboard EV Nautilus to give us an update about what the ship is up to right now. Hi, Erin, can you hear us?
I can hear you. Can you hear me?
Yes, we can.
No? Yes?
Yeah.
Great. I'm alone in here, so I'm actually going to lower my mask if that's okay. I'm alone in the studio and the door's shut, but hello everybody. So I am out on the ship right now, and we're in the middle of a mapping expedition. We're about 150 nautical miles off the coast of California, and we're doing some mapping at the edge of the United States exclusive economic zone. So that's what we're working on right now. You want me to tell you more about the expedition, Megan?
I would love that. And maybe you could tell us a little bit more about mapping in general. Erin is one of our team leads for that effort, and maybe why you love mapping, why you think it's important.
Sure. So we do map with a multi-beam sonar. We have a Kongsberg EM302, which is a 30 kilohertz multi-beam sonar. That's a good sonar for reaching almost the deepest depths of the ocean, which is where we tend to be. We're a typically a deep water exploration vessel. So it fits our needs of being able to map between 200 and about 5,000 meters depth. The sonar sends an acoustic pulse to the seafloor, and that returns. And from the time difference of sending that pulse and coming back, we know the depth of the seafloor. We also get information. The intensity of the return pulse tells us information about the seafloor as well. Gives us some idea of what its character is. Is it soft or hard? So it could help us pick out rocks and things like that. And we also are able to take samples of the water column with the acoustics. So any targets between us and the seafloor that the acoustics run into are also recorded by our system. So we can use that information to track, often we're tracking bubbles in the water column if we're looking for gas escaping from the seafloor, but anything with a bubble in it. So that includes whales with big air pockets, their lungs, or fish with their swim bladders. They also will reflect acoustic energy, and we can see them when they pass underneath our sonar. I am trained as a mapper, so I did a master's degree in seafloor mapping. My background when I was an undergraduate was geology, and I love mapping because unlike mapping topography, this is probably the only view we're ever going to get. We send the ROVs down and we can see pieces of the seafloor, and we can kind of compare that to what we see in the sonar, but we'll never get that full landscape picture like we do with the sonar, and I just find that incredibly exciting. So today, for example, we were coming onto site, coming over an area that had not been mapped before, and went over not one, but two beautiful guyots on the seafloor, these beautiful flat-topped features that were not even, there's no indication of them in the existing estimates of what the seafloor looked like. So we have surprises at every turn. It's really, really fun and exciting. And we just set up a bunch of mapping to do, and we're probably going to be in this area for at least 6 days in this one specific area. Mapping takes time, and we cover big areas, but it does take a couple days. So we'll be out here, we'll be mapping the north. You can see behind me some of the mapping data on one of the screens. You can see some nice rocky topography back there. Yeah, we're just really looking forward to seeing what we'll see underneath the water.
That's so exciting. Erin, I want to make sure we have a ton of time to answer questions from the audience, but I want to ask the first one because I'm like that. Can you talk to us a little bit about, like, you mentioned it takes time. How much time would it take to like map all of the US EEZ? Like I showed that donut around America. Like, how much time are we talking to get that much work done?
Oh my gosh, I wish I had a better estimate. It's taking us maybe 6 days to map something that's, oh my gosh, 100 nautical miles wide by maybe 50 nautical miles. So that's one ship, 24-hour operations to map. Yeah, it's pretty solid square, but when you zoom out, it's really not that much. So it's an extensive undertaking for us to map the whole EEZ, and not just us, the other ships that are also contributing to that effort. So the push to map the EEZ was part of something we've been doing for the whole time I've been on Nautilus with a sonar, but there's been a recent push with an organization called Seabed 2030. And the idea and the hope is that we will map all of the ocean floor by 2030. And just a starting point for the US is to map our own EEZ. We've also been mapping in the Pacific on the Nautilus and in international waters, but now there's this concentrated effort. It's like, yeah, we should map all of that, but my gosh, we should definitely map what is our exclusive economic zone first. So I wish I had better numbers. All I can say is a long time, Megan. It take a long time and many ships, but people are motivated, and we have our ship is contributing. The UNOLS scientific fleet is contributing. NOAA vessels are contributing. So everybody has a push to get their data in, make it available, and so that we get this kind of continuous seafloor model.
Awesome. Thank you so much. Brandon, let's throw it back to you. Erin and I are both really excited to answer any questions that have come in.
Fantastic. Yeah, I thank you so much. I mean, it's just so exciting. My heart is so full hearing chemosynthesis so many times in a talk. That makes me very, very happy. And again, I think it can't be emphasized enough that this union of expertise, both from one field and from many fields coming together, is really the only way this kind of research can get done. So lots of good questions. Actually, one that I thought was really interesting right off the bat. What about clearly the ocean is still that last frontier. How are we doing on smaller bodies? What about like the Great Lakes and things like that? Have we mapped those at least?
That's a really good question. And no, we haven't. We haven't completely mapped our Great Lakes either. And OET and Megan could probably add some in too on this, but we did an expedition last year with Thunder Bay National Marine Sanctuary on one of the Great Lakes. And we were doing some of their mapping, not with Nautilus. Nautilus didn't go there. It was a mobile expedition for us. So we were using an ASV, an autonomous surface vehicle for mapping. And we also, NOAA also contributed their vehicle, the Storm, which is just a smaller mapping launch with a multi-beam sonar. And between our ASV and their launch, we mapped some really big portions, but there's still plenty to be mapped just in that one Great Lake for that one sanctuary, let alone the entirety of the lake. So as with Seabed 2030, that's also put forward a motivation. I think they're calling themselves Lakebed 2030. That yeah, we should be mapping our Great Lakes as well as such a huge freshwater resource and such an important part of the U.S.
Yeah, I would just add, I think that's perfect. I would add that, even charts, and I think a lot of times if students, if you said it wasn't mapped, my first thing, I would pull up my phone and I would look right at that display and I would say like, sure it is, it's right here on my phone. But the point is you zoom in and zoom in and zoom into those, you get less and less resolution up to the point where, a single data point might be making an approximation for kilometers, and if you tried to give directions to your house and when you got within a few kilometers it just stopped and said you were there, I think we would all be pretty frustrated not having the level of detail that we wanted to get the information that we needed. And I think in many places in our maps we're still using either single points like that or even historic points. There are places on the charts of the Arctic that were soundings like put a rock on a rope, throw it over the ship, let it hit the bottom, pull it back, see how far it was from the 1700s. And those are still the modern charts in places. So we really are at a time when technology and exploration is highly needed.
Yeah, that actually gets to another question that was asked. So someone's wondering, what is the big restriction? Now, obviously, scale, right? But are there any kind of technological hurdles? Or is there kind of a future engineering product for the instrumentation to help facilitate this happening?
Do you want me to start, Megan, and maybe you can add on?
Sure, take it away.
Yeah, I mean, it is a limitation. The time and resources is the major limitation. There have been technology advances. Multi-beam sonar is honestly fairly recent. 1980s is when it really became available to normal folks. So that's a while now, but recent in the general history of maritime culture. But we've been making improvements in different vehicles that can go to the seafloor. There was just a Ocean X Prize to try and force multiply the amount of mapping. So people will bring in many different mapping platforms to map at the same time. But we are limited by the fact that we have to go through this medium that is water and that it's quite deep. So from the surface, we can cover so much, but only at a certain resolution. As you get closer to the seafloor, you can get better resolution, but it's a much narrower swath. Acoustics still is thought to be the best way of mapping the seafloor. They're doing a little bit with lasers, with light, but light does attenuate in water. So acoustics has been kind of the way forward as far as I know. So that's kind of on our side, I guess. What we see happening is just more vessels coming online, these autonomous surface vessels, autonomous underwater vehicles, bringing in more tools to do the mapping with acoustics. That's what I see the most of. What about you, Megan?
I think that's exactly right. Part of our 5-year Cooperative Institute program that I mentioned is to work together with other innovative centers and universities around the country to really push the technology some. We have great autonomous underwater vehicles. There are great autonomous surface vehicles. Certainly shipboard systems are refined to a point where there is a lot of operational efficiency there. But how can we get better adding all the toys up. So next spring, we're going to be launching some expeditions where we are looking at multiple AUVs in sequence, multiple platforms all at once. And then there's some really interesting, for students interested in computer programming and machine learning, certainly the logic of how you could design a survey and give certain conditions to a tool that says, if you spot this in your cameras, if you see this type of feature, how could we circle back and investigate that? So that as we multiply, we're not just multiplying things that can map really efficiently, but maybe we can map and also create some logic and create some more selective exploration, really intuition, maybe into a machine. That's probably the wrong word, but to think about how we can start to put the incredible talent that our brains have at pattern recognition, at noticing when something is different, those things that give us, kind of the spidey sense clues when you're looking at the seafloor that something might be different and you want to check it out. How can we also build those into our technologies? And it's happening now, and those advances are coming along. There will be no generation who has explored more of this planet than the students who are in your classrooms. Forget any, if you think about an explorer and you see hat with a raccoon tail attached to it and an oil painting of a man, from the oldie days, that's not who the legendary explorers are going to be. They're going to be your students, because this technology is advancing so rapidly and we have such urgency to what we need to understand about the planet.
That's such a motivating message. And I definitely want to circle back to some of the programs that you have for students and educators. I do want to ask one more tech question I saw came up, which is, you kind of mentioned this a little bit. Clearly right now, this morning, for example, we dialed into a bunch of classrooms talking about the fleet of satellite missions looking at our oceans that NASA hosts. We look at things like sea salinity, ocean topography, but you guys are down here. You're on the front lines. What's the interplay, if any, in between the satellite data and what you guys are doing kind of underneath the water? Do they help each other? Do you guys kind of work on both ends?
Go, Erin.
Well, satellites for us, satellite altimetry is the basis for estimates of the seafloor. So yeah, definitely helpful. And the satellite altimetry has filled the gaps to the point where we have some idea of what's happening on the seafloor. So definitely an incredibly useful tool, and definitely totally worth having. Lets us maybe focus our energies on places. We can map one area a little more quickly if we don't anticipate a lot of seafloor change, so you can always be surprised, and spend more time devoting more time to areas with a lot of rugosity and a lot of features on the seafloor. So on that end, satellites are providing the basis for our mapping data. Satellites are also super important in providing us with our positioning. That's how we know where we are, and that's how we know that the map we're making is right here, as opposed to 100 meters over that way. So on the mapping side, that's where satellites fall for us. And of course, the satellites are connecting us right now.
Yeah, that's a perfect answer. And they keep us safe. All of our sensing of the ocean, certainly, you would not want to go out on. Those were brave people a long time ago who just headed out into the ocean with no idea what they might encounter. Certainly the safety and the operational planning that we have now by being able to look at weather patterns and optimizing when we should be where and when we think we can have the ROVs safely in and out of the water, since we often leave them in for multiple days on end, 24 hours around the clock. It's both for the human safety and the scientific integrity and the, how nice of an experience you're going to have while being at sea. You certainly want to have that forecasting and know that kind of data.
Awesome.
That's so true. Yeah, I kind of take that for granted. We can be constantly checking weather reports. We have scientists at shore weighing in and saying, hey, I see that you're close to this area. Could you go check out this thing over here? It makes it such a different level of exploration than what was available in the not so distant past.
Yeah, I certainly think back to my expedition on the rare instances that we passed by any small little island, and to hear that early explorers somehow found their way to that using nothing but the stars. I looked at that and thought, if you take a quick nap, you would never even know that you had just passed by it. So it is truly astounding how clearly all of this is only possible because of the technology we have at our hands. Kind of switching gears, actually, there are a couple questions about climate change, and maybe you guys can comment a little bit about any work that you guys are doing in the space or how you've seen it. I know that we, kind of in colloquial discourse, talk about it through our lens, right? It's getting hotter, sea level is rising, that affects homes on the coast, these types of conversations. But what about from the ocean research point of view, deep sea, far away from humankind? Are you seeing effects of climate change?
Sure, I'm happy to talk about that. I think it's a two-part answer. In one part, I think you would be totally safe to say, like, we need these baselines. We are discovering things for the very first time. And so you need to understand, like, where we are at right now if you're going to be able to understand how things are changing. And at the same time, to not take anything away from that answer, yes, there are already things that are visible, even in the deep sea. This was not our work. It was a paper that was done off the coast of Chile that detected rising temperatures, even in the deep sea basins there in the subantarctic. Absolutely incredible work to see that over a time scale of only a few decades. That paper was very recent. I'm happy to share it with anybody who has the questions. But certainly things that we're seeing in the ocean is some of the changing chemistry, the same ocean acidification effects that are being seen near shore, the dissolving CO2 in the atmosphere into the water. Certainly the ocean has taken one kind of for the team already. The ocean has absorbed most of the excess heat and a lot of the excess carbon that we've put into the atmosphere. Things that we expect that will change there are things like the productivity and the surface waters. Shifting that balance, certainly of temperature or wind-driven currents or storm effects, changes how much food just sort of rains down. We call it marine snow. It's all the dead bits that come from the sunny surface ocean, end up making their way to the deep sea. That's a massive carbon sink, but it's also a food chain element for a lot of animals. So expecting different patterns, either overall, just it's hard to say there will be more or less, but maybe there will be more in different areas or less. As a result of that marine snow, there is a layer of the ocean called the oxygen minimum zone, where bacteria are sitting and digesting and using up the oxygen of that marine snow particles as they come through. We expect there may be some changes in depths in areas of oxygen minimum zone intensity or distribution, like how wide that layer is. And I think those are a few of those that have already been identified. Certainly things like ocean acidification changing the chemistry of how animals that need to create shells or structures like that coral that creates a skeleton, changing the chemistry of the water impacts many of the things there. And it's, as all science questions tend to be, it is not a satisfying, like, terrible for all corals, great for all corals, but there's a lot of complexity in how different species that we're just learning about and naming and discovering may be impacted. But certainly the deep sea is not exempt. That's what I would say.
I guess you got a couple of questions here looking at kind of again, that complexity of what's going on in the deep sea. Other than, seeing chemosynthesis and these kind of like exciting new metabolic kind of pathways, what else makes deep sea creatures just like wild, just makes them unique? Big question, but a chance to kind of show some of the cool things that you guys have found.
Oh my gosh. There's so many things that make them bizarre. I think about like a food chain where everybody is a slow motion scavenger and everybody is a terrible exaggeration. The microbiologist would be like, talk about the microbes. A lot of the diversity that we're understanding in the ocean is in teeny tiny things, but I'm trained as a coral reef ecologist first and foremost, so I'm going to talk about the big things. And there are some just like truly bizarre creatures in the deep sea and who make their living in strange ways. And a lot of those are scavenging. They're living off of things like this marine snow flux or things that just rain down. And yet they're then recycling them and turning them back into this like larger food chain and keeping those nutrients kind of moving through the world, which is amazing. Things like sea pigs, which are see-through sea cucumbers that walk on little legs. They have a hydrostatic skeleton, which think about just like putting filling up a Ziploc bag like halfway with water and then kind of squishing it from one end to the other. And imagine like squishing that water from one little egg to the other and walking across the seafloor, eating all the little sand and sediment, all the organic molecules and particles in between the sand and sediment, and then passing all that sand right back out. There's things like hagfish, which if you teach younger students, they are an animal with a skull but no vertebrae, and they're just like the grossest Halloween creature in the world. And I'm gonna let you go to Nautilus Live and search for hagfish if you're not familiar. So I think there's a lot of intriguing animals that can be the way to open up a lot of other conversations about life. Erin, do you have a favorite animal that has a unique way of making a living or an interesting story to tell?
Well, I am a geo background, so I focus more on the rocks and don't usually know the names of animals. I really depend on you guys behind me, but I do love sea pigs. I just think they're so funny. I can't explain why. They're just, everything they do is comical.
A very popular one for students, and of course has kind of come up in our question list here, is I mean, I know, again, as I was shocked to see, like when we saw vampire squid and when we saw the all sorts of just kind of crazy new things, but the one everyone wants to know about is sharks. So for our younger viewers out there, biggest shark you've seen, why do we maybe not see as many in our deep sea expeditions? What are they doing if they're down there that deep?
Biggest shark I've seen is a 7-gill shark that was longer than Hercules, so he was over 4 meters long. This is a big shark. So lest we think there are not big sharks, there are big sharks. This was not, we say deep sea and we mean so many different things. The deep sea is so much of the ocean, and it ranges from, a lot of people say the deep sea begins at, a lot of scientists classify that as 1,000 meters. Some people classify it a little shallower than that. And then we work all the way down to 6,000 meters. So 7-gill sharks are on the shallower end of that deep sea range, but in that 1,000 to 2,000 meters, you can find really big sharks, and they're scavengers. They're finding different animals. They're hunting down there. There are fish. The reason you don't see like giant schools of fish, giant tuna, some of these big things are just about the amount of energy in the base of the food web. If you're making your living off of little bits of stuff that are probably being eaten and processed and recycled somewhere as they're falling through the food chain or through the water column before they reach you, it's, I'm not going to say anything bad about celery, but like the nutritional quality of celery is not exactly the same as if you were like eating something with a lot more protein and a lot more calories. So by the time you get down to the deep sea, you find animals that are often sort of in slow motion. They metabolize slowly, they reproduce slowly. They don't have like big beefy bodies. You see a lot of fish with these like long, skinny, elongate bodies without carrying a lot of muscle mass. And if you were to draw a shark with a long, skinny, elongate body without a lot of muscle mass, you get a 7-gill. They're a long, thin animal, kind of a big, bulby Muppet head, but otherwise a pretty narrow body. But we also see little sharks. We see glow-in-the-dark cat sharks. Check that out if you are interested in sharks.
I did see a shark on the last expedition. It was a little bit shallower, probably around 500, 600 meters, but it was super cool because we were focused on sampling. So everyone was looking in the front of the vehicles. And I looked up to one of the cameras off the starboard side where they were going to put the samples. And there was a shark kind of creeping up on us, checking us out from behind. And if you weren't looking in those cameras, you would never even know that it's there. It's just very sneaky, very cool.
And if you like sharks, check out Nautilus Live, and then there's the education tab, and we have all kinds of fun stuff there. But one of the things that I love are the video playlists, and they are all kid approved YouTube playlists, and there are different themes. So if you just want to check out sharks, check out our Sharks and Rays playlist, or our Maritime History and Shipwrecks playlist, or I think there's even like a octopus and squid only cute cephalopods playlist. But those are some of the great spots just to lose yourself in the deep sea.
Yeah, you guys even have like highlights by year. So if there are things that you wouldn't even know to look for yet. So, watching some of those highlights, you can just kind of be blown away by some of the wild discoveries that are found, and then kind of investigate further from there. Mm-hmm. Since you mentioned the education opportunities, the last question that everyone wants to know about, how the heck do I get involved, right? So I know that obviously COVID made some big changes to the educators and students on board. But can you tell us just a little bit about the opportunities for students and teachers going forward?
Absolutely. So there are lots of ways to explore along with us, from the live stream and our social media channels to our live event series. So similar to this, we've also had some great conversations with different members of our team, how they got interested in that kind of work. So you can check out those features to dive in and meet some of the different personalities, maybe explore the type of career you might be interested in having with our career videos or our BuzzFeed quiz of what job you'd have on Nautilus. Also, if you want to join us at Sea, we run a couple of different types of programs. We have a paid internship program for students from community college, undergraduate, graduate school, or recent graduates. So wherever you are in that education journey, we run programs in ocean science, to be a data logger on board the ship, in seafloor mapping to work with Aaron and discover these features on the seafloor and learn to acquire and process that data. We have an ROV engineering internship if you're interested in robotics and engineering, like the vehicles, Hercules and Argus. We have a video engineering and filmmaking internship, which if you are interested in how we tell the story or the satellite communications and technology elements of how we are doing this work. And we also have a navigation internship that's offered in partnership with the Coast Guard Academy and the Naval Academy. Happy Veterans Day to folks in the US. If you're interested in that type of service career, there is also a pathway there. For educators, if you are a formal or informal educator, and that can mean writer, artist, teaching anywhere from K to gray along the spectrum, and you are interested in helping introduce the deep sea to your audiences, we run a science communication fellowship that brings you out to be the expedition communicator. It's how I got involved in the program for the very first time, and it's how Brandon joined the Corps of Exploration as well. So that's a year-long program where you work as a cohort with other educators from around the world and get to go out on expedition for a period of time. So all of the information about those programs is available on our website. We will not be opening applications this fall, but you can check out those next fall for the next season coming up ahead. And certainly on the website as well are all of our education resources. So if you're looking for anything from Nautilus Bingo, like you're watching the highlight videos and you want to play a little game along the way, or try a design challenge, or bring in a national standard aligned lesson for your classroom. Those are there and searchable by topic or searchable by grade level as well.
Yeah, and if you're an educator watching this now, a reminder, Megan and I will be back this weekend. The registration for that is on the JPL Education website. If you guys want to hear more about these opportunities to go through some of the activities from both Nautilus and JPL Education, we'll kind of talk through them, model a couple for you guys so that you guys can take them to your students. So with that, we'll thank this incredible team for this incredible opportunity. Thank you guys so much for this great talk. It really just promotes wonder, truly, to see that this is something that everyone can do, right? Everyone can access this online. They can get their hands into it. I think it really is something that puts a spark in me for the future of STEM. So thank you guys so much for joining us. Really appreciate it.
Thank you, Brandon. And thank you, Aaron. Go mapping. Have fun out there.
Yeah, thanks for sticking with us. Thanks for signing us in. Good talking to you guys.
Always. Bye, everyone. Thank you.
All right. So to close out in the last few minutes, I'm going to show you guys just a little bit about some of the opportunities for these educational activities at JPL Education. As you'll see on my first slide here, the main place to go, our first stop, is jpl.nasa.gov/edu. And you'll see at the top there are several kind of categories for you guys to play with. So our internship opportunities, kind of similar to the ones that Nautilus offers, we take hundreds of interns a year. Again, due to COVID, that's kind of been reshaped, but if you have graduating high school students or beyond, all the way through graduate school that might be interested in working at JPL, this is where to go. And if you're more in the K-12 scene, then you'll play with this teach and learn section, where you're going to find things like our classroom activities, our at-home projects, and etc. On the second slide, you'll see an example of this. One of the activities I really like for our younger audiences is what I call precipitation towers. And this is a kind of representation of data of rainfall, of precipitation for different cities across the world. And we have these sheets already made, and young kids get the chance to look at, is there seasonality? Are some places drier than others? Generally, we don't give people Pasadena or really anywhere in Southern California, since they finish first. For our older students, on slide 3, you'll see an activity based off of some other satellite data we have, like graphing sea level rise. Because we have all of this NASA data, we can pull this. We can put this into lessons where kids can authentically interact with some of the data that's being collected from these satellites. So this isn't hearsay. This isn't just talking about it. They can actually access the real scientific data that we've collected over decades. On slide 4, you'll see a brand new lesson that our awesome team of chemists and geologists put together, thanks to the incredible help of our web designer. And this is looking at some of the things that you heard mentioned by the Nautilus team, which is the geology down there is really important too. This kind of often forgotten science that doesn't get its fair shake. But now I'm learning. I'm a convert myself that geology is really just slow chemistry. So knowing that, all of a sudden I've started to love geology. So some really cool activities there, looking at how our crust is formed, why we have the diversity of rock structures that we have, and just kind of a cool way to model some of this geochem. On slide 5, you'll see a site that I really hope all of us will at least visit once. Again, whether you're in the classroom or not, this is climate.nasa.gov. And this is where all of that data about Earth science is collected in one spot. It's just your quick go-to for all things climate and all things Earth science. And it's really an amazing website. What you can see at the bottom of the picture here is what I call like Earth's pulse. So how are we tracking things like carbon dioxide in the atmosphere, temperature, sea level rise? And by clicking on any of these, you'll actually get access to just kind of quick tidbits of data, and you can deep dive and go further. So really, really great place to start for your own personal edification, as well as to have students, again, manipulate data. There's nothing more compelling than actually getting their hands in the data themselves. They shouldn't have to just be talking about credible resources or some unknown scientist says this. They can do this. The data is written for them, and I think it becomes that much more impactful. On slide 6, you'll see that beyond just these activities, we have just a multitude of other resources for you guys. So we have things like the teachable moments. This is in the news section where, every once in a while we'll write kind of a deep dive, still written for the general audience, but exploring some new feature of what's happening at NASA or JPL. This year on the West Coast, things like wildfires were running rampant. So we, got together and wrote an article on that. So these are kind of chances to not just get a topical understanding, but really look a little bit deeper in terms of what JPL is doing. On slide 7, again, you'll see if you really want to take a look at this teach section, this will be what we'll focus on primarily on our educator workshop session this coming weekend. And the thing I really love about this website is the fact that you guys can kind of use these drop-down menus to get exactly where you want to go quickly. So of our hundreds of activities, all of which are 5E lesson planned, worksheets are already made, answer keys, we're translating many of them into Spanish. You guys can quickly do a search or pull down a drop-down menu, say, I just want ones on oceanography. I only want ones that are for grade 6. And this way you can kind of really get to where you're going as quickly as possible. And then on slide 8, you'll see, because of the fact that we're in this remote instruction environment, the Learn section is a great place for either kids to explore on their own or to have teachers kind of point students to. And these are lessons that mirror the ones in the teach section, but are written a little bit more for like a student-driven exploration. So a little bit more like, step-by-step kind of get the wheels turning before you put them out into the open to explore on their own. So I think that's really been a huge asset for the remote instruction, because you can assign this to students and say, show me the final artifacts of your project, instead of this kind of traditional, teacher-led model. On slide 9, I'll tell you guys that, again, this is only just the tip of the iceberg. There are so many other amazing education resources. If you go to Learning Space, you'll see these kind of groupings of different thematic kind of lessons, activities, things to read, multimedia kind of videos, pictures. We put all those collections there for you, as if you know what you're looking for, this is everything we have in that space. And it can be a really great way to kind of explore a little bit further. So finally, on slide 10, I'll tell you guys, again, there's just no end to the number of resources we're putting together. We always are working with teachers to put together more exciting content for you. And I hope you guys will play with these websites and hopefully find something that sparks your scientific interest or the interest of your students and your kids. So with that, I'll close out for the day. I thank you guys so much for joining. I hope you really enjoyed today's session. And if you want to learn more, please check out our websites, as you've seen here, or the websites of the Nautilus team, the Ocean Exploration Trust. Really big fan of their education materials too. And we'll dive a little deeper, cheesy pun very much intended, on some of our collective resources this Saturday for a teachers only workshop. So thank you guys so much. Really appreciate your time. I hope you guys will join us next month for our following session. Have a great night.